Adrian and Lenardic will speak today on thermal evolution and continents.
Thanks. You'll see I won't actually get to that, but I'll try to set us up for it. Just by way of a wee bit of a heads up, we switched out computers. Some of the images are a little darker than I thought. I don't think it will be an issue for most things. The people who will be most upset are those of you, like myself, who like lab tank experiments. They came washed out. I know that. If there are some other images that aren't clear, let me know, because my perspective here is a little tilted. Last Friday, we got into what I would consider kind of a brainstorming discussion. I quite enjoyed that. We threw some ideas out, saw what would stick, kept our critical eyes out, but also were willing to get a little imaginative. One of the things I particularly liked is that some of our discussions stemmed from one single number. And if you recall, and if you weren't here, I will just tell you this, that number happened to be 40 kilometers, which is the average thickness of the continental crust at present. And it was kind of interesting that we started pondering the potential significance of this number. It could be other things. How different would our planet be if it was other things? And we even went into a direction I quite like. Is there some mechanism, or if we study the Earth, we always know it's probably more than one, some combination of mechanisms working together that might, I don't know if this is right or wrong, regulate that thickness to 40 kilometers. If it goes a little higher, it goes back. If it goes a little lower, it goes back. I find those questions kind of interesting, and by way of setup, there's another number that comes out of looking at continents, another length scale number. You probably can't see this. I'm about to draw. This is a world topography map. I'm about to draw the borders of continents, accounting for continental margins. Some portions of our continents are underwater. This will make it easier to see. We get something like this, and if we look at the length scales on average over the planet, we find that about 40%, not precise numbers like Greg, I round up a little bit, is continent, about 60% oceans. For those of you who teach, I teach an Earth Science 101 class. I give that topography map and I say, give me some observations about the Earth. This is one of the most popular ones. I think it's second after the Earth is round. Oceans, continents, 40, 60. When I'm allowed to speak out loud, mostly at actually planetary science meetings, but I think it's appropriate here, I do ponder this number, the significance of the number, what does it mean? Is there some mechanism that sets it, or is it some myriad of factors at work that something could have been a little different and it would have been different and that's just what we're seeing? Another way to phrase that pondering is to do a little thought experiment, a Gedanken experiment, and imagine, and you'll see this is a squishy experiment, but I think it works. Imagine the things that in your mind make our planet our planet. And then let's scale that by a planetary difference-orometer. How different would the planet be if X, if Y, if Z? And we can think about that in terms of how much continents we have, how much ocean basin we have. The perhaps somewhat trivial end members here, and don't take the actual sweep to be meaningful, I'm just sort of getting end members. We can imagine at some extremes we'd be on a very different planet. How different? Interesting question. We can imagine somewhere in between here, maybe not so different. And then, well, let your imagination run wild. I can't really tell you the answer to this. I'm going to set up one avenue into it. But it's an interesting question to ask. And if you were here for my questions to Lou, you can see that I actually sort of get drawn to these issues. It comes into different things in terms of the habitability of the planet, living on it. Consider the end member. Would we be on something that's not Earth-like if we had 80% continents? I don't know the answer to that. It's an interesting question. I like to ponder it. Whenever we think about changes, changing something, we're thinking about change, motion, whatever. And ultimately, we should track that back to an energy source at some level. Nature is kind. Most of us in this room, in our lifetimes, only have to worry, at the end of the day, about two energy sources. One, the power of the sun. And when we talked about weathering and climate, we talked a little bit about this and how the distribution of continents and oceans affects that. Continents, whether they might draw down CO2, what happens if we had less, ocean pathways might change. Something we didn't mention, the albedo of land and sea is different, that might have an effect. Interesting issues. I actually want to approach the problem not from the top down, but from the bottom up, and consider the other main energy source. This might have been a little washed out, but I've tried to project actually a world heat flow map under the continents here, with high heat flow below the ridges all around here. That's the other main heat source, the Earth's internal energy, decay of radioactive elements, potassium, thorium bound up in rock, energy associated with the formation of our planet, accretion, differentiation. It started hot. And continents affect that energy source as well. Let me take that off, and there's the map. This is fairly well dated now from Pollock et al. It's a compilation. It's a long wavelength average. The particulars, not so crucial other than we have heat getting out of the ridges. If we look at finer scale, and I'm sure Claude Chopard will talk about that, we can look at the continents and ask ourselves what that tells us about the interior. I actually want to think on the broad scale. And in thinking on that broad scale as scientifically curious people, as the collective, we've approached the problem by focusing on some parts first. There's nothing wrong with that. We can focus on the heat flow coming out of the oceans. And generally that's done within what I'm going to call a convection framework, half-space cooling or plate model, if you like. And by way what hopefully now is review, we've talked a little bit about this. The idea is that at a mid-oceanic ridge, this is where plates form. They spread, material comes up, decompression, melting. We form what will be the plate of plate tectonics. As we move off that ridge, we have this heat, ultimately, which will be transferred out. We have macroscopic motion, chunks of rock moving. And that macroscopic motion is associated with heat loss. That is the definition of convection. Heat transfer involving macroscopic motion, as opposed to diffusion, which would be conduction, as opposed to electromagnetic rays, which would be radiation. Now, we can argue about the particular form of convection in the mantle, but I am hoping that we're on the same page that we should not, at this stage, be arguing about whether the mantle convects or not. The oceanic heat flow data, topography, that all tells us that. That's where it's coming from. It is tied to data sets, as Kent said. We have a conceptual framework, and some of us add numbers to it, where we have this thermal boundary layer of mantle convection. The layer across which the vertical heat transfer, the final path mantle heat takes out to get to the surface, is in the vertical by conduction, by diffusion. That's the definition of boundary layer, the transition between those two mechanisms. Greg talked about rheology a bit. We can expand on this. Apologies. I'm not going to think about water right now. We'll just go with the classic oldest model. Material at some point becomes stronger, and we have a layer of long-term strength. But this is a convective framework. At the other extreme, we've approached continental heat transfer. This has been done, not exclusively, but for some of us, within a conduction framework, steady-state geotherm models. And what's done is a region, a generally broad region, is chosen where we can get some heat flow measurements. I suspect Claude will talk about that. You can see how they're done. It's not trivial. We have that measurement. We have to construct some model of the upper crust. In particular, what is the radiogenic heat concentration within there? The heat sources, how much uranium, potassium, thermal conductivity. Maybe the lower crust gets a little harder to get there. We have to use other data sets to try to constrain it. We didn't talk about this for cratons. People ask me afterwards. It's worth thinking about. Maybe in the discussion we can. There is this stable mantle lithosphere. What heat sources does it have? What is its thermal conductivity? Let's assume we knew all the thermal properties for the upper, lower, and layer here. We don't, but let's assume we did. We could then actually say, okay, let's take the surface heat flow, construct a conductive geotherm through here. Whatever we get in terms of the flux predicted at the base becomes, in this approach, it would be a free lower thermal boundary condition that accounts for mantle convection, but we don't have to solve the convection problem per se. Does that make reasonable sense? Yes. Okay, now hydrothermal circulation in some portions of the crust will act. I understand that. I've also ignored magmatic events. They can move heat very efficiently. I don't mean to insult the people who study magmatism or melt generation. I'm going to actually start with just these simplest things, and we can build on to that. And hydrothermal circulation gets even more complicated. But we want that base. And that's his story. If you want the seminal papers in this, please ask. What I want to think about is putting it all together. As E.M. Forrester once said, only connect. Sometimes that's the hardest part. Yes?
It looks like the heat flow at the mid-ocean ridges is greatest in the southern hemisphere. Is that actually an observation yet?
This is a very filtered out map, and I don't know if this is held up. Claude, is that true? No. I think that's just an artifact. I forget what wavelength they actually used here. Purely illustrative.
It's basically seaflow.
Yeah, purely illustrative. Yeah, but the actual heat measurements here, I think that's a lot of the smoothing that's coming from. I forget what degree this is at. When we link these things, I'm actually going to introduce some, which I guess is maybe more engineering technology, but if you're interested in heat and mass transfer, it's good to be on the same page. This becomes what's referred to, and these are just words we use to communicate with each other, a conjugated heat transfer problem, when more than one heat transfer mechanism is at work and they're interacting with each other. That's just the general term. And we want to approach that. Here's a cartoon cutaway. It's a cartoon, a conceptual idea, very simplified. Let's consider that we have continental heat transfer. We have conduction over the upper portions. And notice I've assumed that these are stable regions. Deformation will change things. We'll build on that, but let's start with the simple. Maybe we have conduction in the lower region, but also maybe some convection, drips, delamination, all these sorts of things. The other side, we have plate overturn. Again, by definition, convection. The particular form, that's something we study. And that dominates oceanic heat transfer. I'm going to make a claim that this is affected by and affects continental heat transfer, that this is, in fact, a coupled problem, and we need to consider how they link together. That's really going to be the essence of what I talk about. And at some other level, let me tip you off. I'm told it's good to have modest goals. I have a modest goal. If you've read literature about continents interacting with the mantle, in particular mantle convection, you will run across the phrase, continents act as thermal insulators above the convecting mantle. At least one or two of us have run into this. That's an easy statement to make. My goal is to try to get us in a position where we can actually understand what that statement means as it's used by different people in different contexts. And you might see a thematic here. I'm always kind of fascinated by the things that seem so simple at blush value. Oh, continental crust, 40 kilometers, let's move on. That actually lead to kind of some deeper issues. And if you recall Mark Jelinek's talk, which I think drew just a little bit of confusion and controversy, some of it revolved around this issue, and that's the only one I want to address. And understanding it affects the climate and all things, that's great, but keep that in mind. That's my modest goal. Solid Earth heat transfer system. This is everything, the entire Earth. I haven't drawn convection down to there. Understanding the behavior of the solid Earth is something I suspect many of us thought about, and many of us have our own ideas about what's really important here. The asthenosphere is important. Rheology is important. Phase change is what happens at 410, 660 is important. Thermochemical piles at the base of the mantle are important. Now, if modeling was a true democracy, which is, let's say if I or Thorsten or Shiji, before we came up with any sorts of models, just went around and asked all our colleagues, what should I put into my model? You can imagine what we'd have. It'd be a complicated mess with every factor in there. And keep something in mind, substituting an ill-understood model for an ill-understood physical process is not progress. So I want to kind of work our way up to this. And I'm not going to be democratic, and from here on out, I'm sorry, this is a dictatorship. I want to focus in on the simplest relevant system that gets at the interaction of something conducting here, some lid making a boundary layer thicker, and something convecting there. I'm going to strip this down. If you are easily offended by modelers leaving out your favorite mantle dynamics effect, I will offend everybody in this room. Everybody. But I don't care. I think I have that goal. I want to get to that goal. Here's my thought on the simplest relevant system that captures that. Imagine I have a tank, a 3D tank that I bring into this room. Imagine it's a plexiglass tank. Imagine I can put some fluid in it that I will let convect. Imagine that I can put some lid into it that I can measure its thermal properties and then heat it from the bottom, cool it from above, and see how much heat gets out. There's another reason I chose this system, to try to understand these basics. I don't have to imagine this. You can build this. You can do the real experiment. I'll show you some real experiments. I'm glad I didn't choose mostly experiments because they're a little washed out. But you can develop your intuition on how this simple system works. And you can ask yourself, if we can't understand this simple system, what are the odds we'll understand that one? They're pretty low. That's going to be the focus. There you go. If you look at this and you go, I am inherently bored, I'm sorry. I've tried to set it up. It's pertinent to the real problem. We'll come back to it. I'll try to connect it back. But we want to understand that aspect of the heat transfer. In fact, let's strip it down even more. Let's go with the simplest thing, the one that will really let us get at what we mean by this word insulation to begin with. Let's say I just have a fluid tank with a lid on it. That's it. That's very simple. Some terminology and some definitions here. Let's say I have some control, the word control is nice, on the depth of my tank, and 3D on the extent into it. Let's say it's the same, consider a cube, and some control on the depth of this lid I will put on. It doesn't deform, it just sits there. And I can prescribe a surface temperature. I can have a cold water bath that circulates with ice cubes in it. Some of you might know we really did that. We actually did it here at Berkeley. We can have a hot bath that tries to maintain a constant temperature at the base. We can characterize the properties of the fluid I'm dealing with, thermal conductivity or diffusivity if you like, of the lid, thermal conductivity, the viscosity. Here's my offense to Greg. Let's consider the viscosity to just be one number for now. Single value. Scientists love the Greek. Iso viscous. We'll build off that and we can move on. We can't consider the density to be one value, or else this would be a very boring experiment. But let's say we know the thermal expansion of our fluid. We know the density. We can define a Rayleigh number. Recall what Shiji talked about. And really, this is the simplest type of convecting system you can get other than smacking that lid onto it. Those are all in black, and I put them in black because people of my ilk like to call these control parameters. Things that in the experiment, you as the experimenter have control over. You know the value of it. You adjust it, you tweak it, and you see what happens. There are other interesting things that we don't have control over that the system, or in the real world, nature, determines from the dynamics. In this case, it's that temperature at the base of the lid. And I'm considering averages for now. We can consider variations, but what will that be? I'm not setting it. It will be determined by the heat transfer properties of the system. The average internal temperature. Also, there will be a boundary layer here, a conductive boundary layer. The material here can't move, it can't convect. Diffusion will be a mechanism. There will be a boundary layer. A little different than at the solid Earth system because it's seeing a rigid boundary condition, but it will form. And the final heat transfer path out of this for the fluid will be in the vertical conduction all the way up to the top. And by smacking this lid in, you might make that path a little longer. We like to talk about thermal resistance, how much resistance to the heat ultimately getting out. That's a word I'll use. If you're not familiar with it, I'll use it now. And if we change that, we're changing how easy it is for heat to get out. That's at the core of what insulation, in a strict sense, means. What do we really want to predict? This would be the coolest. If you tell me the control parameters, can I predict how much heat gets out of the system? Now, you might see why engineers have interest in this. There are real-world insulation systems we care about. We'd like to predict that. I want to build a little intuition here before I jump in. It's going a little bit in reverse. I'm going to show what I'll consider some experiments before I show the theory. The theory should be tested against the experiments. I'm glad I chose the numerics, but let me tell you, everything I'm going to say can and has been done in real fluid tanks. I chose the numerics because I knew visually they're a little easier to see. Real-world experiments have real-world mess. It's harder to see things sometimes, but everything will hold. So here is that convecting fluid. It's isoviscous, surface temperature, base temperature. There's the lid thickness of imposed. There's TL, there's D. Color palette from the darkest colors, the coldest, red to the hottest. There's the interior temperature somewhere there. This is a very high Rayleigh number, very vigorous convection, about 10 to the 10th for the experts. For the non-experts, this thing's really swirling around fast. A back reference to Shiji's talk. I suspect Shiji showed you something like this. Yes? Even smaller than that. Okay. Yeah. When you blow it up, your graphics get a little weird. This is just classic Rayleigh-Bernard type convection. No lid. Just the surface temperature, base temperature. The Rayleigh number defined using that total D scale and this total is the same between the two, using the control parameters, the same. Notice you have these thermals coming off the boundary layer. Imagine if you smack the boundary layer and it's hot, heat diffuses in. Eventually, thermal expansion, things become buoyant, plumes are sent off. Similarly for the other side. And they start to mix in and homogenize the system. They thermally well mix the system. And if I were to take a temperature profile, I'll show you some. If I walked across there, other than when you hit these thermals, you would see one well-defined mean temperature. Now, again, to back connect to things that might be interesting, when we talk about one potential temperature for the mantle, we're assuming something. We're actually assuming, we know the mantle's convecting, we're assuming there is some well-mixed region. That's the essence. If we draw some profiles through here, so let's say this is the depth, and I take the average temperature. In numerics, we can get this very easily. You can do little tutorials on it, and you can do this on a laptop. In the lab, it's a little harder, but we can. We'll notice this well-defined interior temperature. For the simplest system, it happens to be 1/2 the top and the base temperature. Things are well mixed. There's a symmetry from top to bottom. We have the thermal boundary layers. They're not perfectly straight, but I've drawn them that way for idealization. And this symbol is somewhat of a universal symbol in heat transfer literature for the thickness of that thermal boundary layer. This is active. It's always overturning. It's always convecting. There's just that average thickness. And we have the lower one. If we imagine this case where we've added some insulation, you can let your intuition go now. Hopefully people have some intuition about insulating things. When you buy your first home, you will develop some of that intuition. If you don't have your first home, if you're in dorm rooms, maybe you have it. Conceptual is good, right? Conceptually, right, you think insulation will make something run hotter. That's fine. Why is that in this case? Notice in this case I've been judicious in my choice of D. I put it right where the thermal boundary layer thickness should be in this case. What that means is some layers got to form below there. And in this case, I've forced that last leg of heat, right, its path to become longer. It's a longer path out. That makes heat transfer harder for the system. That's the essence of the insulation. You can also imagine, hey, what if my D wasn't that deep? What if I had a thinner layer? Maybe the effects would be a little different, maybe not as pronounced. That would be good intuition. What if it's deeper? Is there some limit? That would be good intuition. And just coming back to some notation, I used sublayer here only in the fact that this delta is kind of traditional for thermal boundary layer. So I wanted to stick with that even in the insulated system. But that would be the little sublayer, the active layer where you see the plumes dripping down. You might even say, based on this analogy and the stuff Shiji talked to you about and the stuff you learned very well, because you learn very well. Shiji's a good teacher, I know that. You might imagine, what if I consider, okay, some analogy here. That stuff's not convecting, but below here. Maybe I have something similar. So maybe the internal temperature here won't be 1/2 of the top temperature and the base temperature, but maybe of this lid temperature that these plumes are seeing, these thermals are seeing and mixing. And that's not bad intuition. Of course, you're going to want me to test this to see if it's true, but it's a good starting point. And if you think about this, the problem now kind of breaks down into, what's that? Right, that lid temperature. Because if you get that, you can get the heat flow out of the system. It's conductive. It's a simple conductive path. I know the thickness. I know the thermal conductivity. My problem is solved, or as theoreticians like to say in their jargon, it's closed. And when I say it's closed, I have enough information to come up with an expression for Q as a function of control parameters, the things I know. Does that make reasonable sense? Good. Intuition's a good thing. Of course, sometimes you want to go further. If I came to your house and I said, the $20,000 you're going to spend for the insulation I'm going to put in, my intuition is telling me that will cause your heating bills to, let's see, they'll probably go down. You don't have to be the nerdly scientist we all are. I say that with great respect. You can just be anybody, and you probably say, I kind of want a number. I want you to quantify that. Some of the scientists in this room of my ilk maybe get carried away sometimes by asking others to quantify. But if you can, it's worth doing. If you can't, that's okay. In this case, you can. In fact, I won't leave it completely as a homework problem, but some portions of it I am going to. Let's say we don't rely on numerical experiments. Let's say we don't rely exclusively on lab experiments. And I ask you, on a homework problem, tell me, what is the average heat flux, average, out of this system, average over time and average over space, as some function of the control parameters, as some function of what you know? For a lot of us who do modeling and try to understand experimental results theoretically, we spend large chunks of our day doing just this. That's it. That's the goal. You can do it. You need to assume a few things. The world's always that way. Let's make some assumptions. Keep in mind the limits the assumptions put on us, and I'll come back and try to remind us of that. Let's assume the entire system tends toward, a little bit of a jargony word here, I'll explain it, statistical thermal equilibrium. What that means is that the average heat flow into the lid from the convecting fluid will have to be equal to the average heat flow out of the system, and I've assumed strictly bottom heating here. Will have to be equal to the heat that comes into the system from below. Notice this system does not set that heat flow, it sets the temperature. The convecting fluid, how it adjusts, will determine the heat flux. That's long-term statistical equilibrium. It's not on average heating up, it's not on average cooling down. That's what that means. We can adjust this if we had internal heat sources, and we'd have to consider that term as well. But a lot of what I'll lay out will carry over. Let's also assume, we don't have to, but a nearly linear thermal gradient across the lid. So a line in terms of the temperature and on average through this dynamic boundary layer thickness. For the experts in the field, I could put that as an error function. It wouldn't change things. It would just make the algebra a little more tedious. That's all. The last one, I'm going to have to ask if this has been covered. This one comes from, and within any fields that involve fluids convecting, now that's mantle convection, that's magma chamber dynamics, that's the atmosphere, you might run across this. Did you cover this, Shiji, at all? Okay. If you remember what Shiji said about boundary layer Rayleigh number, we were just using different words for the same concept. This idea goes back to a very famous paper by Howard in a very obscure journal. I forget even what it was, some And Michael might remember. If you want the reference, I'll give it to you. And it's been used by many people since. It's an idea. It's an idea that the local thermal boundary layer Rayleigh number, remember how Shiji defined that? And for me, right, that's going to be the active one, this portion that's going through stabilities and sinking, remains on average near a constant value, that its thickness on average, averaged over the spatial domain, averaged over time, has some well-defined constant value. That's the essence of what Howard said. Now, here's where my experimental friends and I go, wow, that's an icky experiment. I apologize. I tried to show, this is a real experiment, a real fluid tank with a real lid on it. I actually could have chosen better ones. I chose this one because we happened to actually do it right here in Berkeley, and in Berkeley, Mark Jelinek and I did, so I wanted to show it to you. Michael even came down every now and then and gave us a Zen-like nod, which I hope meant it's worth doing. But we sat and we watched it. Now, we're laughing. But actually, Howard, how he got his idea, how a lot of theoretical ideas come to people, they're not from reading some math book or being, handed it down from some mathematician above. A lot of times you just look at the system. And if you can ever do a real experiment, that's why you should. Just look at the system. Look at what it does. Develop some intuition. And Howard drew little cartoons like this of the boundary layer. He noticed, right, heat would diffuse in, we'd get some boundary layer, and then a plume would detach. And you'd thin it out. And then it diffused back. And he noticed on average, that kind of averaged out, so this thickness here remained at a constant value. That's direct observation. That's what he used for his idea. And from there, right, that's the concept. The rest becomes algebra. If you accept this to begin with, then you can go through the argument. Boundary layer thickness is a variable, but has a well-defined mean thickness. Recall Shiji told you that the onset of convection in the entire fluid can be determined by marginal stability analysis for the whole layer. Are the forces driving convection greater than the ones resisting it at some value that we need to know? That can be done locally, and that's where the local boundary layer comes in. Let's say we do the same idea for the boundary layer itself. Define a Rayleigh number based on the average thickness of this boundary layer, the average temperature drop across it, the thermal properties of the fluid, and ask when does it go unstable. This is the boundary layer Rayleigh number Shiji went through with you. Hopefully it's somewhat familiar, yes? If you get the concept, that's good. Get that. The temperature is a little different here, right? It's the temperature across the boundary layer itself. We don't know that a priori. And we can just do some algebra. This is just algebra to relate this boundary layer Rayleigh number to the Rayleigh number defined for the entire system. That's it. And if we assume it stays at marginal stability, if it gets too thick, things drip off. If it gets too thin, it diffuses back. If you think my talk is willy-nilly, maybe you see some connection with ideas about the continental crust in a different way. There's something that regulates it in this case. On average. That gives us an expression for what that boundary layer thickness should be. Why do we want the expression? We need that last one to, as I said, close the problem. Because, right, we've got to solve for TL, TI. We need enough to connect, to backtrack, to say, okay, there's the boundary layer thickness. I can match that to the heat flux coming out, to the heat flux going in. And I can knock out unknowns, or I can relate them to other unknowns to get a final closed form expression that will let me make a prediction about how much heat is getting out of the system. Those are the assumptions that go in. Ready? Exercise left to reader only if you're interested. If you're interested in this sort of stuff, there's enough information here for you to go through, and quite literally, you're just going to algebratize the physical assumptions I've made. You can get the expression I'm about to show you. You can check my algebra. Looks a wee bit messy. Not too bad, really, I mean, comparatively. So here's what we're looking at. The non-dimensional heat flux out of this insulated system depends on the thermal conductivity, and I've normalized this to the thermal conductivity of the fluid. So if it's 1, they're the same. That's all I'm saying. Temperature at the lid on average, temperature at the surface on average. I'm getting average values. Thickness. This TL, this expression is a little bit messier. It involves the Rayleigh number. Now, the Rayleigh number here I've defined in terms of a control Rayleigh number based on the total depth, the one I have control over. There is an effective Rayleigh number, the Rayleigh number defined from here to here, that affects the fluid properties. And that actually went into this analysis. But you can solve for it. dd, that is a constant. In these types of problems, you will often, if not always, see a constant appear. It's sometimes referred to as a geometric constant. It accounts for the fact that I know maybe if I have a longer convection cell, things will be a little different, shorter, if I'm spherical, if I'm not. Generally, that constant is on order 1. This theory doesn't get at it.
What happened with the units?
I've non-dimensionalized everything. So I've non-dimensionalized the temperature by the control temperature from top to bottom. I've non-dimensionalized that thermal diffusivity by this one as well. And then I've had the Rayleigh number as well. So it's a non-dimensional. Sorry? That is also non-dimensionalized by the depth of the fluid layer. Yes, that's what falls out of it, yeah. You can do it. You can check my algebra. It's coming from this effective Rayleigh number. There's other ways to check it, and we will. I'm pretty sure I didn't make a mistake. And other people have gotten the same result. This doesn't look like maybe your classic physics 101 when you solve for a closed form equation that you can express the unknown as a function of other things. That's termed an algebraic solution. This one's a transcendental solution, but there's no numerical approximation. You can do a lookup table. And there's enough information here to predict everything you need in principle. I could have made an algebra mistake. Maybe the assumptions are wrong. We don't know that. We need to test this. There's different ways to test it. I told you we could test it against a lab. I could show you that. I'm glad I chose not to. We can test it against numerical simulations as well. And I'm using numerical simulations now in the mode of numerical experiment. I'm going to run them to see what happens. They're based on conservation equations, mass, momentum, and energy, that we know very well. They have, or we think apply very well through various experiments. We also know that they contain some nonlinearities, if you like, nastiness, which makes them, under most general conditions, unsolvable in closed form. So to solve them in closed form, we have to use some approximations, and I've used several. These are the assumptions that come into it. I can go through the simulations that don't make those approximations and see what happens. So there's a Rayleigh number, convective vigor. There's the D, no lid. I add more. You see what happens. Increased Rayleigh number. Increased. And maybe you see your intuition coming into play here, right? At higher Rayleigh number, where this boundary layer is already inherently a little thinner, the relative effect of adding a lid is greater because you're increasing it more to that final temperature. And we can go through suites of these and vary all the parameters to see how well the efforts at a closed form theory match the experiments. And we've done this with lab tanks. So there's theory, there's simulation. Rayleigh number, this is a non-dimensional heat flux out of the system. I non-dimensionalized it. Different depths. You can see at the higher Rayleigh numbers, greater convective vigor, things moving, things, I'm going to use a term here, mixing very fast. It does okay. When theory matches experiment, we jump up and down and go woo, but we should also look at places where it doesn't. Over here it does not. And there's a reason for that. Howard's criteria doesn't apply to lower Rayleigh number convection. It assumes very vigorous convection. In fact, just to give some jargon words, it's educational, maybe so we're on the same page. It's expected to be asymptotically correct as the Rayleigh number, as convective vigor goes to infinity. That never happens in the real world. We have to compare to experiments to see when that transition is. And in this case, it's around there. There have been efforts to modify this for lower Rayleigh number. If people are interested in that, you can ask me. And where the Earth's Rayleigh number now becomes interesting, because if it is down here, you might say, well, at present you need to modify it. If it's up here, you say maybe you're okay. And we can go through longer boxes. Does the essence of what insulation here means make sense to you? Yes? Okay, good. Because I think in Mark's talk we got into the effects of continents, which aren't really, strictly speaking, some of them, tied to insulation in the sense that the thermal diffusion path is made longer. For example, continents affecting where subduction is, or how things override it. They'll have geometric effects on the pattern, too. For my own thinking, I like to separate those out from discussions of insulation. It lets me isolate the physical factors. Maybe some of you are triggered by some of the discussions we had. Well, what's the next step? Right, that's the simplest. Now, I'm hoping, right, this was a bit whirlwind. You can read these papers, you can try the exercise. You might appreciate that even that simplest one isn't trivial. I mean, there's some work we have to get to that. What happens if we do that? This gets closer to the real-world problem. We don't have the lid cover all of it. We have it cover only a part of it. You have some intuition about that. I hope nobody lives in this type of house anymore where you have just one little heater there. Maybe you have centralized heating and we insulate our houses to keep the heat in, to lower heating bills. And we know the thermal properties of this stuff. We can characterize it. We can use even fancier jargon words than I've used. Two people are giggling. They know these problems very well. Some of us ponder them for engineering issues. But let's say we have some heat source, it's heating the room, it's mixing up very well. You can ask yourself, hey, is it a big deal or a small deal if somebody goes up into my attic and removes some insulation? And you can ask yourself what your intuition says. You can ask yourself, is it a linear response? What do I mean? I remove half the insulation, the temperature drops accordingly, three-quarter accordingly, and it goes like that. If you study nature, you know that linear is the exception to the rule. It's not perfectly linear, but you can ask that question. You can ask yourself, is it considerably colder here, warmer there? Am I going to see variations? Run it through in your own mind. Intuition's good. Again, there's nothing wrong with intuition. There we are. Again, I'm just going to show you some experimental results using numerics as an experiment. There, and this got a little bit dark, but there's the full lid. The Rayleigh number defined for the whole system depth, the control parameters. Same. There's the depth. This L now, that's the extent of the lid, so it's covering 60%. And you can see the changes. More heat gets out, it cools. Makes sense? Yes? There's the thermal boundary layer for that section. That's that last diffusive path. It's thicker here because of the lid and also that sublayer below. If you recall our discussions, again, trying to come back a little bit to the real-world system, of continental lithosphere, that it's always thicker than oceanic, and that it might be stabilized by some chemical layers, that's the analogy. The thermal path changes as well. Now, I will tell you I've modified my talk a little bit. And because I didn't know what Mark Jelinek would talk about and what stemmed from it, I thought might be good to come back to. There it is with no lid. Now, Mark made you be keen observationalists, and I made you answer questions about numerical simulations that were far more complex than this. I won't do that because I think you're noticing something already. That is, if you said, hey, Adrian, could you put a thermal probe in there and one in there on these different sides, and I can, and you looked at the large-scale temperature variation, what would you see? In this case, you see nothing. That's it. It's the same bulk temperature here and here. None exists. Now, on average, this whole thing certainly is running hotter than this whole thing, and that is an insulation effect. You have made that upper boundary layer, on average, right? We've got to do the average across the whole thing. Thicker, that is pure insulation. It's not related to geometry. It's not related to where subduction zones, sinking things, and rising things are. That's the pure insulation effect. Yes?
I'm curious. If you look at this diagram, this lid, I would say maybe on average temperature below the lid that's probably higher slightly, because you have upwelling overall.
Yeah, okay. This is a valid point. If I actually took it over here to the upwelling, and notice this is extremely high Rayleigh number. The thin jets are very, very thin. That's right. If they were a little bit thicker, you'd start to see that, but you would see the temperature variation only in the thermal jet itself. It wouldn't be generated at the length scale of, and this is good to separate out, at the length scale of the lid itself. That would be something due to the lid itself. Does that make sense? And the Rayleigh number is important here, just so you know, right? Higher Rayleigh number, more efficient mixing. And I've chosen the high ones here. I'll come back to the lower ones. Excellent point. Now I got to take an interlude, a super interlude. All right, for those of you who are incredibly bored with the vagaries of heat transfer theory, although I will tell you the entire Earth system relies on it, all geology does, so you shouldn't be completely bored. I'm going to take a super interlude, a supercontinental interlude. I want to talk about a mantle convection model that is not a typo, that 3 is not a washed out 8. 1935, we as people, scientifically curious people, were thinking about convection in the mantle. The mantle is a solid. Do never go too far with the analogy and say it's a convecting liquid. Greg will jump on you and say there's a difference between fluid and liquid. Subsolid is convection. Before plate tectonics theory kicked off, which is about, 67, 68? Supposedly the advent of mobilist ideas. We had considered convection in the Earth's mantle, and Peckerus considered it in 35. In fact, he had a model. What was the state of supercomputing in 1935? Anybody?
Computing was a job description.
Somebody actually got it. Thank you. You were a computer. Collectively, people would get together to solve problems in hand. That's pretty much what you're saying, right? You were part of a computer. That was it. Peckerus didn't bore graduate students. He solved this analytically. And you see my love of analytics. If you can get it, it's insightful. Here's what his model said. He said, well, let's say we got continents on one side of the planet. He thought about them being insulating. He also thought about them with a little complexity. I don't think what I'm saying changes too much here. That granitic crust is enriched in heat-producing elements relative to basalt. He also included that it might heat it up. And he imposed that as an effective boundary condition on top of the system. That is, right, what the system does at the interface. The system determines. I went through trying to get us to get to that. We don't know that. And solved for the flow that would result in the Earth's mantle. Upflow, downflow, that. That was it. When continents are all clumped together, what word would we use? They're kind of super, yeah, okay. This started within, I guess, early geodynamics, a big train of papers. There's many you can read that go under this general idea of supercontinent insulation. As far back as I can track it is to Peckerus. If somebody knows a further historical one, let me know. I get sometimes obsessed with history. I don't know why. Just grass is greener, right? You can only solve equations for so long. Some people picked it up. Perhaps some of you are familiar with Holmes. He actually used it in a book of his as a conceptual cartoon. I actually put this up only because Shiji and I started talking about Bott, somebody who got a little bit forgotten in the mantle convection game. Did some interesting stuff in 64, worth a read. Elder as well. I shouldn't get too personal, but if I have a hero, Elder's one of them, just in the way he did things. Don't read Elder papers, I guess everybody says. If Adrian likes them, that's okay. Don Anderson is coming to talk to us. He actually pushed this quite a bit. He tried to tie the conceptual idea to some databases. Kent would appreciate that. And then along came Mike Gurnis, when I was a student. And actually, Elder did some numerical simulations himself. They were a little coarse, a little rough. Mike did some of the first full numerical simulations of convection with a continent and found these sort of things holding true. And rather than go into it, if somebody wants to correct me on this, and there are some people who have read the literature, I think this is true. This kind of started a cottage industry. A lot of people started running numerical simulations with continents on them. And a lot of it revolved around supercontinental insulation ideas. It really kind of took off. If you read through this literature, I hope I'm not overgeneralizing, but in general, you will see this impression that the insulation effect only kicks in once the supercontinent forms. Now, I'm not saying that's right. In fact, I think that's completely wrong. It sets up all sorts of questions, some that Michael asked of Mark. And that's what originally got me thinking a little bit about it. It sort of gestated for a while. And now more recently, this general question, and now you see, hopefully we're coming back to Mark Jelinek's talk. Is a supercontinental thermal anomaly possible? Not is continental insulation possible, but is it possible in a way that sets up, this is why Shiji's question was good, a thermal anomaly that is at the scale of the continent itself. So you don't have some well-mixed temperature completely through this. You would actually have, Mark mentioned this a little bit, if I tie it to the real Earth, a different potential temperature below the supercontinent than below the ocean. That's not what we're used to thinking about today. Well, maybe we think about it a little bit, but it would be different. Is that even possible? Now, these simulations claim to have it. Some of the ideas had it. But techniques get better. Some simulations from Nico Coltis et al., 2009, said yes, following this trend. There are many others. But perhaps the more disarming thing, if you've been involved in this, is that some started to say no. Heron et al., and I could have added before this O'Neill et al., and the second O'Neill et al. Is Lenardic. I myself had started to wonder about that. Now, what do you do in a situation like this? I think in all our fields, we're generally sometimes confronted with, two people with different ideas about the same thing. Is that fair to say? Yeah. And you can say, okay, I'm going to argue this side. I'm going to argue that this side is right because it's got to be one, it's got to be the other. I haven't learned too much in my life, but I've learned a few things. Maybe not. Maybe both are valid solutions, and you'll see them under different conditions. And in fact, that was my starting premise. If there are two courses of action, I'll always take the third. Maybe they're both possible. I did this for a couple of reasons. One, O'Neill and Lenardic. I think Lenardic's not a stupid person. Coltis, I know Nico very well, and I actually asked him about his simulations. I think they're good. I think they're fine. We can argue about that. That'll be technical. But none of these groups did anything that I can see fundamentally wrong and sort of a sloppy mistake. And I'm glad Thorsten will check me on my algebra. That can happen. Nothing that I could see. So what's up? I want to do a simple Gedanken experiment with numerical simulations. Again, the simplest system stripped down completely. Convecting layer, isoviscous. This one is mixed heating, but that's not going to change things too much. There are some heat sources internally. Cold sinking material, at some level an analog to the upper oceanic thermal lithosphere. Not a great one, we don't have the rheology, but we can think about that. Rising material. One of the beauties of numerical simulations compared to lab experiments, you can interrogate them. You can ask them all sorts of things. What's your temperature here? What's your temperature here? What's your temperature here? With lab experiments, that's a little harder. But in this case, I can say, what is, hey, numerical experiment, the mid-depth temperature as I just march along here. And that's what I'm showing you. And it's non-dimensional from a maximum temperature of 1 at the base to 0 at the top. And that's what you get. Notice when you see this, and this comes to Shiji's question, when you see these sinking thermals, you do see a temperature anomaly. There as well. There's the rising plume, if you like. But notice this background. There's a reasonably well-defined average. It varies over time. I'm showing you only one time slice. I can run it over all time and get the total average. Good? Nothing too different, nothing too radical from what Shiji told you, from what I've told you about this system. Let's go to the partially insulated system. There's the lid. you can see things look hotter. Let's do the same thing. Let's not just think about the bulk temperature, but let's think about the temperature as I march across. That's what I get. There's the big cold one. You're seeing the tail of that cold one. You're seeing the plume there. Notice what you're not seeing. You're not seeing a temperature anomaly on that length scale, on the lateral length scale of the continent itself. And that's when people say supercontinental insulation thermal anomaly. That's what they generally mean. To separate it out from plumes coming up. That's a different thing. Make sense? Yes? You can check it. You can say, what if you're not so super? 2 continents. March down. Same thing. You can do this ad nauseum. It's already ad nauseum, Adrian. You can do it for various situations, and I'll just tell you I have. And you come up with something that looks like this. There's the average. Now I've actually taken the average across the entire system. The bulk background, 0.671. 1 continent, 1 supercontinent, 0.804, 0.808. That's at one time. If I go over all time, these come about to the same value, about 0.8 something. The entire system is running hotter, not just locally, and it doesn't matter if it's a supercontinent or not. That would be the one that says supercontinent anomalies are not possible, yes? Insulation is still going on. Continental insulation is still at work. What's happening? I didn't tell you something. I didn't tell you something about the boundary conditions. I didn't for a reason. How do I deal with those lateral side conditions? In this case, they're a little bit of jargon wraparound. Imagine I took the system and wrapped it around on itself. So what comes out one side goes in the other side. That's kind of a trick. What it allows is for the convective pattern in the mantle to move relative to the continent. To drift if it wants to. I don't lock it. I could get the same trick if I let the continent move. And we have checked that. Now, right, that motion, that allows for, I'm going to say it again, mixing, efficient mixing. You're not hampering it. What if I did this? Let's say I don't make those wraparound, but I say fluid can only go up and down on the sides. I'm going to constrict what the pattern can do a little bit, the convecting pattern. And what if I do this? Just to see what happens. What if I also prescribe, usually we don't describe internal boundary conditions like this, but we can if we're careful. I just say, look, over this portion down to, let's say, 80%, 60%, I can set it. I'm not going to allow for any lateral velocity, but I'll allow the vertical velocity to do what it wants to do. Does that make sense? Yes, sir.
What happens if you take like maybe some sort of running average of the temperature across there? Because it does look like there's more cold down mountains.
Well, you start to see them, yeah, you see them here. You see them where you have these anomalies. At the mid-depth, if you average this over all time, that is long time, that's the long running average, you don't see significant variations. Let's be clear on significant. If it's about 10 degrees, I'm not going to count it. If we're getting toward 50, 100, I'll count it. You will see, but they're always going to be due to exactly what you said, where the blue is, where the red is. Does that make sense? And I'm trying to separate that out from insulation discussion. That comes into play for the Earth, too, where our subduction zones. But we want to be able to think about them separately. If you take the running time average, it's actually even evener. Even evener.
Like maybe a windowed average of
Oh, if I did it even smaller, little patches?
it does look like there are more cold down mountains.
If I did this in terms of little patches, this system, if I allow it to wrap around, it's going to change once I change these conditions, so maybe we'll come back to you. If I allow it to wrap around and mix, those kind of move. So on average, it actually averages out. So maybe at one point in time, you see something a little colder, but over the time average window, you don't. Does that make sense?
Yeah.
Okay. No.
When all these models, when the slabs go down to the mantle, they get bigger?
This is completely isoviscous. It's very idealized. I'm not including any rheologies that might allow for thickening or anything like that. So that will come back when we say what's the next level of sophistication you might want to add. Yes? No phase changes hampering anything, nothing. I said I'm going to be a dictator and I'm going to offend you. I just want to look at the insulation effect. That's it. Yes. Yeah.
How do you define anomaly? Because we have the plume in the supercontinent. It looks like there's a slight temperature swing.
Right. So that is a thermal anomaly at the scale of the plume length scale itself. How wide is the plume? Right. I'm in the mid. That's what I'm seeing right there. I'm seeing that boundary layer. I can also define, I can say, do I see something that is at the scale of, and maybe the next images will show you this continent itself. Is the entire mantle, even away from plumes, on average hotter than it is there? And I can separate out those anomalies, but that's important. You have to define them on some scale. Good? Okay. I'm going to force this. I'm going to see what the system does. Before some modelers in the room yell at me that I'm prescribing what should be formally, in a dynamic sense, an output, the system should get whatever configuration it wants, and I'm forcing it. Just, if your modeler is going to do that, be aware I know what you do. If you've never done that, go ahead and throw a rock. No one's throwing a rock. It's a value sometimes, right? You sometimes see a derogatory, you're doing hand of God. Let's say you force a plate motion onto it. But depending on the question you're asking, there's nothing wrong with that, right? You can get some insight. So I'm doing that. I just want to ask about an end-member question. What would happen if I do that? Here's what happens. Now, how do I define anomaly? I got a different definition. Now I got much hotter at a length scale much greater than any thermals here. That would be what most people traditionally, from Peckerus on, think about a supercontinental thermal anomaly. And the system allows for that. It allows for it by me forcing some things, forcing the convective pattern, and not allowing for any lateral transfer from here to here. In fact, I'm forcing this half to act as an independent system and this half to act as, some sense, an independent system. Remember when I set up the problem, I said coupling is important? I think most times it is. I think most times they're not independent. Continents do drift. There is motion. There is mixing. This would be an extreme end member. It is an end member we do not see on the present-day Earth. As far as I know, there are no observations suggesting this. Could it have happened during supercontinent time? That becomes the issue.
For the timescales on these?
I'm about to show some timescales. Yeah. And in fact, all the debate, debate's a good thing, yes? Yes. Almost all the debate Shiji and I will get into will be related to timescales.
Is the boundary condition really at the middle there? Is there a gate that goes all the way to the bottom?
No, there is the boundary condition from here to, let's say, 80%, and that's variable. I actually say no velocity in this direction, that's it. Yes, below. And then now you're seeing that this system is saying, I can't handle this anymore, and some of it's leaking out. That will be different if I have it up here, and I wanted to set this up because this is a way to ask about how much cutoff you have. Does that make sense?
Yeah.
It's idealization, but I have control. Remember, control's good sometimes. Intuition. In fact, the T-shirt I'm wearing, they had a song called Control. So there's the average temperature now with this supercontinent. Again, marching through, you see there are some plumes, and maybe this comes to Ben's question. This is what I would define as a large-scale thermal anomaly. It's at the scale of this lid itself. Much hotter. Come into the ocean side, we see sinking. But away from that, another well-defined temperature. Long-time running averages. I can take long-time running averages. This is what you get. The initial state, the long-time running average, you average through. Thermals move all over the place. You get a well-defined background temperature. Now, again, when we talk about a mantle potential temperature, we're inherently assuming something like that exists in our planet, in the interior. There's what happens after I put in if you call it a gate, that's great. I haven't been able to think of a good term for it. It's just an arbitrary cutoff. Timescales. This is so idealized relative to the real mantle. I don't want you to take timescales too literally. We'll come back to it. But I can put a timescale to this. And I can put a timescale to it relative to a timescale. How long does it take on average the convecting system to overturn? For the Earth's mantle at present, that's about 10 to the 8th years. If I do that and say, what time frame am I looking at these profiles for that, noting that this is highly idealized, there are the timescales. What is this telling you? That the system is feeling that change in mixing on about an overturn time. And hopefully that makes sense, right? You've stopped the insulation from the continent side coming into the ocean. It's going to adjust. It's convective, so it overturns once, and you're going to start to feel it. It won't be complete, but you'll start to feel it. And that's where you start to see the thermal anomaly forming. If, again, gross idealization, I put in some representative temperatures just to give us some intuition, and you should ask me, right, how those simplifications affect us, and that's what I want to set us up for so we can discuss that. If that's 1350, then you get 1433, 1283, 1358. Who wants to do some math in their head? You do. What do you notice? Okay, and that's a good one. That's due to the volumes of the reservoir, 60% on the ocean, 40% on, oh, very good. Might be different on a different planet. What else do you notice? What if at any point in time you said, what's the average temperature across the entire system? Add them together. What do you notice? It's the same. It's the same. And it has to be the same if no heat source enters the problem. This is Michael's question that I wanted to address. There is no heat source no new heat source entering the problem. All that's entering the problem is the lateral communication between here and here. Are these acting as completely separate convecting tanks, or do you have a channel in between them? I don't know. Oh, sadly, the physical oceanographer left. Cold lake, warm lake, I put channels between them. Similar idea. That's the essence of the idea. Keep in mind, coming back to Louise's question and probably what Shiji's thinking of, this gives this effect the best chance of working because I've completely cut things off. Completely. It's an end member. I think some of the confusion, or as I got it from Mark's talk, he showed you the end member. I don't think the end member necessarily applies to the Earth. It does depend on these time scales. All right, now a little bit of jargon. When the system is going through this adjustment, it is not in thermal equilibrium. Right? Portions are heating up, others are cooling down. That makes the problem a little harder, and we're still working on those time scale aspects. But those are the end members. So the globally average mantle temperature remains constant. So I'm going to move through this a little bit quicker. Let's say I wanted to do some scalings for this. Well, for this regime, this end member, and again, to get here completely, it takes billions of years. So you can say, okay, that's fine. But I can actually ask myself, what should I get? Complete separation. This is an easy problem. And it's odd, actually, we approached it last and not first. You're saying that this layer just acts like just basic Rayleigh-Bernard convection. Pick your favorite scaling. Howard's, Claude's, Michael's, whichever one. This side, everything I showed you from the lid case. That's it. It's saying it acts that way. And then I just do I'm glad you noted the different reservoirs, an average based on 60, 40, or whatever number I put in. That's it. This one's a little harder. This is the one that assumes, I kind of like this. I don't show a lot of animations, but woo. You can do the Gedanken experiment. I think it's easier to think about in this direction. If I went in this direction and I opened this sluice, I guess I'll use the water analogy, you get complete mixing of these reservoirs. And again, mixing occurs on a convective timescale. Timescale it takes for overturn. That's where you're getting this 10 to the 8, that you can have a significant effect on a timescale that's faster than, Shija used the word secular timescale. That's Y in this case. You can actually approach this one too through a, oh man, the jargon's getting deeper, parallel link thermal network theory. If you're interested in the reference, ask me. It appeared in an engineering journal, so you might not have seen it. How does it work? Well, we need this. I'm going to assume that something like this is valid in the n-member cases, so that in the mixed case, to some good approximation, the average temperature will be the temperature with the lid, temperature without, weighted by geometric factors. That's it. I don't know how many of you have seen analogies between thermal networks, fluid networks, and electrical networks. I'm really the only one? Okay. This is a beauty of nature and a beauty of nature tied into our math. When you mathematize those systems, the structure of the equations looks almost the same. Nature's been kind. If you learn how to solve one sort of network, if it's electrical network, flow of electrons, you can solve it for the flow of heat. You can solve it for, originally it actually started with fluid pipe networks. And that's all I'm using is that analogy. I have some thermal resistance here that depends on the thermal thickness of this boundary layer. I have some thermal resistance, that last path of heat getting out here, that depends on the depth of this lid. If we want to tie this to the Earth, this would be, let's just say, at the chemical lithospheric thickness. If I wanted to use this to say how do continents affect heat getting out of the planet. There would be this sublayer below. I suspect Claude will talk a little bit about that as well, a dynamic sublayer below the continents. Again, if you want sort of a so what for Earth, right? If seismologists measure down to where there are significant temperature variations and geochemists measure where there are chemical variations, you shouldn't see the same thing. We might want to know how different those are, and you need some thermal theory to get at that. And then the temperature drop. This is a little different than most networks because this isn't fixed. This is the interior temperature relative to the surface temperature. And the problem gets a little nastier because that interior temperature does depend on the resistance of the lid. Right? If I make it thicker, it gets hotter. Makes it a little nastier. But you can still solve it. You're going to have to trust me on this in the interest of time. It is published. Consider the end members. The resistance across the lid zone. Some people go back a little bit to Physics 101, potentials and flow. If they're acting in parallel, and that's what that lateral mixing would say, then you have to treat the resistances this way. And then you also have to account for the difference between resistivity, a value with no lateral length scale, and resistance and the area of continents and oceans will also come into play. And you will process this equation in no time, I'm sure. Just one little thing in terms of your favorite scaling theory. These are numerical simulations without the lid that I need, that we ran to very high Rayleigh number, 10 to the 11th. 512 finite elements for the experts here, 512 here. You need to go some pretty high resolution to test some of these theories even without the lid. And you can see even there, if you're nitpicky, and for those of you who publish in engineering journals, you know engineers are nitpicky. The theory's not doing a perfect job, but it's close. I'm glad Greg talked. 3.53, whatever. 1/3 not perfect, but close. So I'm just going to use that. I could adjust it, or you could adjust it. You could go to a higher order theory. Ta-da! That's it. There is the complete prediction for the total average heat that gets out of the system as a complete function of control parameters. Extent of the lid, QF, which I get here, Q lid, which I get here, which has the thermal properties of the lid, the depth of the lid, TL, which has the Rayleigh number, again, defined across the whole system, everything else, the messy geometric constant. I suspect you know what's coming next. Got to test it. Got to run more simulations. I got to vary the lid. Boom, boom, boom. I can go through them. There's the result. I asked you, do you think it's linear or nonlinear? Lid extends 0, so there you got full insulation. Let's say you remove 20%. That's how much more heat you get out. It's not a linear relationship. If you look at this most vigorous convection end limit, you see the theory does pretty good. Again, it's breaking down at the lower Rayleigh numbers, and Howard's criteria is breaking down. And the reason it's breaking down is that the boundary layer, when it sinks or not, doesn't just depend on local things. Plumes coming up might actually affect it. That gets a little messier, and that's something some of us are working on. But at the highest Rayleigh number, it does okay. The theory is kind of cool also in that it lets you predict locally heat flow. Here's a prediction of the local heat flow getting out of the stable continent side, the ocean side. You can see we do reasonably well. Hey, Adrian, the world's 3D. Yes, it is. Most recently, Katie Cooper has led the charge in extending our work into 3D. This is a 3D box. Again, relatively simple in terms of the material properties. Sorry, Greg, I'll relax that. A conducting lid of some specified shape, some specified depth. 2 blocks, 4 blocks, keeping the total area the same in this case. See what happens. We can compare that percentage of total coverage here for different configurations, single, 2, 4, right? And that's the super, non-super, super, non-super. You can see there's not too much variation. That's because this system still maintains lateral mixing, complete mixing. Theory does okay, some time series plot. See, it actually, once you get to 80%, this number wasn't chosen when I started this discussion off the top of my head. Once you get a lot of continents at the top, the configuration starts to matter. And it starts to matter because it actually sets, this is going to get a little bit more technical for some of you. If you're not enjoying it, don't worry, you can blank out. When it gets small, it actually sets the pattern of convection. You force the convective pattern and you force the wavelength. What you're seeing is wavelength effects, not pure insulation. The continent's affecting the pattern of flow. And in this case, you might notice this shows how uberly nerdly I can be, a beautiful, in the sense that this is classical, it was predicted by some theoreticians, convective pattern set up at what normally at this Rayleigh number shouldn't allow for it, but the continental blocks are stabilizing it. So trying to separate those effects out, that's something we're doing now. But the theory seems to be okay, at least first order. In terms of temperatures, this is, and maybe this comes back to some of the plume discussions and things like that. This is the average internal temperature across the whole system. And then in black, we track temperatures at any given time, sublid temperatures below the lid. Notice here, sometimes you will see these overshoots. Those are plume heads. They do come up. But right, it's not penetrating all the way in. It's not at the scale of everything. It's not that local insulation effect. And interestingly enough, it's actually when you get the forelids that you start to see that become more prominent, not the supercontinent case. And that's actually because you're locking the patterns in. And if you lock the patterns in, remember I said mixing, that actually tends to inhibit mixing as well. And that's why you start to see the anomalies coming into play. Okay, good. Well, super interlude 2. Back to where we started. Remember I said, this is what I wanted you to understand. And understand it at the idealized state, the simplest one. Just getting at mixing, convection.
So this is really just changing part of the surface boundary
Yes.
artificially in a stagnant bed.
Yes.
Which is, I don't want to be nitpicky, but it seems like allowing these things to move could like potentially be very different.
Well, in this case, I am allowing it to move. That's right. No, for the 3D simulations as well. Yeah, the wraparound, there were wraparound conditions on this side and this side, so you get, people hate this, it looks like a torus, I guess, geometrically. So the mantle flow pattern could move in those cases. No, not the continents, but the flow relative to the continent. And that's what's really, I think, important is the relative motion between the two. You can let the continents drift as well. We can go and do that, and maybe I'm wrong in saying that that's what the most important one is. But letting the flow pattern move relative to the continents allows for the mixing. Letting the continents move might allow for the mixing as well. Letting the continents move might mean that some of these patterns we see might not be stable over time. That's a question I can't address this way. Continents, I'm going to make the claim, and I have made it in the literature based on fancier models, always insulate the mantle. Always. Because they always make the boundary layer somewhere thicker than it would be without them. And I hope seismologists will go, duh. That's what you guys have been saying. I listen. I listen. Always. And by the definition of insulation, it should always be there, supercontinent or not. My inclination is most times in the Earth, because continents do drift, because the Rayleigh number is high, it's distributed throughout the entire mantle. So the entire mantle is running hotter. I'll try to wake up geochemists. This actually says the potential temperature of the mantle, if you removed continents completely, based on what seismologists tell me about thickness, the potential temperature of the mantle drops by 150 degrees. No one's shocked. That's kind of a big implication, isn't it? Yes? No? That's what it says. It says continents are affecting the potential temperature of the mantle, and that area will affect it as well.
Adrian, a counter to that is if you remove all the continents, you have to put all the uranium and thorium back in the mantle.
I have slides for that, yeah, actually. I said just remove them. I didn't say put them back. We've addressed the put them back problem. Yeah, we've addressed the put them back problem. Will you be surprised if I say there are trade-offs? We can talk about them. But you need to consider it. You need to consider the insulating effect and the depletion effect. The other one that comes into play, right, if you remove radiogenics and you put them into the continent, they make the continental base a little hotter. If you want the jargon, that actually increases the insulation as well. So that trade-off becomes very important. Not completely mapped out by my thinking if you want a new problem to look at. If you cut it off, you get that. Boom. Average is tame. Fancier models. Greg. Temperature-dependent viscosity. Power law 3. I'll switch to 3.5. Ductile shear zones forming here. There's the continent. Thermally mixed. I can do this, which I've shown you. I think something that Thorsten was getting at in terms of drift, stagnant lid, and maybe a little bit of Shiji too. In this case, if I don't put this artificial subduction zone here, but I force the continent to stay fixed relative to the mantle flow pattern, that's sort of what you were asking, Thorsten, yes? Okay. Then you see that you do start to get a thermal anomaly here. And in fact, within cell mixing, because this is one convective cell, is not as efficient as if you have cells moving through and mixing with each other. Also, I've been sneaky. This has a depth-dependent viscosity. The Rayleigh number here is a little lower. I will tell you, if I crank up the convective vigor, or if I go back in the Earth's past, that thermal anomaly starts to go away because the mixing becomes efficient, and you can map that out. Why did I put that up? I said I know Nico, and I think he's a good guy, and he did things very carefully. Here's one of the simulations that suggested global warming of the mantle was possible. It made quite a, shall I say, stir. It was called global warming of the mantle. I told Nico it should have been called local warming. You'll see why. From the origin of supercontinents. So there's a supercontinent that forms on this mantle convection simulation. This is purely internally heated. And everything I said holds for internal heating as well. If I make the boundary layer thicker and I got radiogenics that need to get out, and I've made it harder for them to go across the path, the only way to get to thermal equilibrium is for the system to heat up. It would all carry over. And what they saw was that if you track, like I have, I guess, average suboceanic temperature, average subcontinental temperature, here's a function of the time before these continents are going to form together to form a supercontinent, the distance between them. Notice the changes. Notice the time scales, right? 200, 400, about 200 million years from there to there. If I take the thermal network theory and just say what they're seeing is a switch from well-mixed to a switch when this long-scale flow pattern, degree 1, many of us love degree 1, driven by the continent, becomes locked to the continent, something that's allowing the system to unmix a little bit, I make that prediction. And it works. This is what you need for that to happen. So in Thorsten's world, right, you got to fix this entire system. You got to have this happen in the Earth, or you have to think this did happen in the Earth, or you have to think slabs surrounded the planet. But it is possible. And notice this anomaly. That's when Mark Jelinek was showing you, about 150 degrees over the time scale of Pangea assembly. We're not inconsistent between those. And remember, Mark actually pushed that to say, what effect would that have on the climate system? Notice also the ocean. It's going down. You're cutting it off. You're affecting how much is getting out of the ridges. Would also come into play. Now, just because two numerical groups are consistent, you can say you're both wrong. The way we would both be wrong is not in analyzing this system. It's in the applicability of this system with its assumptions to the real planet. That's the issue now. So I said you can do these. Fine. I'm going to jump, 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 jump. You can do real experiments. There's me doing an experiment. There's Mark. There's the experiment. We confirmed many of the things I was saying. We looked at them for temperature dependence. And that is where I end. Thank you. So I did change a little bit on the fly, and because I thought it would be good to maybe try to get some insight into what Mark was saying, and I hope that wasn't tedious for some of you, and I hope it was beneficial. But the questions that come up are in this sort of exercise that we want to go back to what I suspect everybody wanted me to talk about, and sorry, but some understanding is good. The word understanding means quite literally to stand under, perceive a structure, and we can add to that structure. What do we do next?
Early in the series, we had a talk by Kent and a talk by Rick Housen, and they showed us continental growth curves.
Yes.
Have you run the thought experiment that says that we, at 4.4 or thereabouts, had a 60% continental blanket, and we've always had it?
I have gone beyond running the thought experiment. I've actually used the theory and put in every single growth curve I could get a hold of to see what happens. That paper's out if you want to read it, also in an obscure journal.
Tell us what happened.
A lot of fancy, complicated things happen. I'm actually not going to go out on a limb because it's like Craig thinking, do I really want to get into this? You do have potentially significant effects. The growth curve can affect the Urey ratio, which in thermal history is kind of a big deal. How much heat is getting out of the mantle now relative to how much radiogenic is being produced. Different continental growth curves affect that Urey ratio in different ways. And in the thermal history game, we sometimes get fascinated by trying to match a Urey ratio. They make different predictions. My thought was, could you use these models with the growth curve to make some thermal predictions to add a, if you like, data set to constrain the growth curves themselves, to say this one's more likely, that one's more likely. Within the trade-off so far, I'm not 100% convinced I can do that, but that's ongoing research. But it does have a non-trivial effect on how heat gets out, that partitioning of heat. The thing we don't do, just to let you know, recycling back in, I don't know the numbers to put in, so I kind of do it arbitrarily. Does that make sense?
So you're saying you cannot exclude those models still?
I would not be 100% comfortable doing that still, based just on thermal history arguments. I was hopeful I could. That was the start of the exercise. But again, I said it before, knowing what the answer is not is knowledge. It didn't work out that way. I can lean toward. My leaning takes me toward more the linear growth side. My leaning. You're a little closer to matching the constraints. But there are uncertainties in the thermal constraints, too, that you can hit within the uncertainties. It's the real world. Why do I sometimes go to lab tank experiments? Because sometimes the real world hurts my head. I can at least explain a lab.
So sorry if I missed this, but it looked like for most of your models where you have the supercontinent present, you always had the plume under the supercontinent. Were there times when you didn't have the main plume under the continent?
Yeah, quite many times. In particular, things would drift around. Once you get very small continents, actually, you go kind of the other way. Once you're at the close to the length scale of the boundary layer itself, you generate downflows at the edges, and they merge, and you actually start to generate cold sinkers below the continents. Once you make them big enough, supercontinent enough, the preference you're seeing is a preference. It's a preference, statistical preference, but not always. The insulation effects I talked about and everything I talked about here works completely if there are no plumes at all. I can go completely internally heated system. We did those as well. I'm not saying plumes aren't important. I'm just saying for the effects I was focusing in on.
Was that dependent on the Rayleigh number, or was that dependent?
Where the plumes are, yeah. Greater Rayleigh number, if you push this to these asymptotic limits with a lot of mixing, then no. I mean, there's no super plume type structure that we think about on Earth. It's just very thin thermal jets. Maybe more for magma chamber, vigorous convection, yeah.
So if I'm thinking of this as modifying the scaling from plate tectonics to stagnant lid, then I guess I have a couple of sort of prefactors, right? One is the 40% coverage, and then there's also some sort of prefactor as to this not truly being a stagnant lid in terms of affecting the long-term heat transport. Do you have a feeling for what that factor is?
The geometric factor is a little hard to get at, and I'm not being wimpy here. I'm not being wimpy. We would have to know, for given control parameters, what characteristic wavelength or pattern does a convecting system go to do this in theory? We don't have, as far as I know, a theory that does that even without an insulator. You can have different patterns at the same Rayleigh number. That's what makes that problem tricky. If I know the pattern, if I know the wavelengths, I can approach it and then it's not too bad.
I guess what you could do is you could just compare the theoretical scalings we have for plate tectonics, whatever that might be, with a stagnant lid, and then see if you add your rigid continent floater, where in between those two extremes are you?
Well, you know, in some sense, the theory we developed, you can actually say it does that, right? It's mixing the two together.
Right, but can you give me a feeling for this factor for, if it's not just geometry, right? What is the other, scaling factor in between there?
Which is the other scaling factor? Perhaps I've missed this and got fixated on the first one you asked. What's the other one? The potential that the continent is deformable to some degree?
Yeah, I mean, ideally you would want to know that. But I mean, just based on the simplified experiment.
Okay. The one with the continent deformable to some degree, I will just, in the interest of time, say I don't know. I don't know. Depends on how deformable, how far away you are from that end member. My sense is it will not be dominant compared to other uncertainties, let's say the viscosity. Why do I say that? In particular, let's say over the lifetime of the last supercontinent where we have a lot of observations. The other observation any student will give me is you can fit the continents back together like puzzle pieces. So they're not falling apart. They're not completely gooey. They're not completely deforming. That assumption of some over that time scale, maybe not for the entire Earth time scale, is probably good enough that the uncertainty with that is going to be lower than uncertainties I have, let's say, with plate reconstructions or if I want to tie it to heat flow. That's my intuition.